This is lecture 9 called SomeAtomicPhysics. It's part of a mathematical physics course on quantum mechanics at senior level. First author of the text I'm using is Davies. Here's the text. I do this every chapter. So quantum mechanics, it's the second edition. Two authors, Paul Davies and David Betts. When it says atomic physics, so it's the quantum mechanics of the atom, but in reality most of this chapter is about the quantum mechanics of the addition of two angular momenta. How do you add two angular momenta in quantum mechanics? And it's quite, in fact, I can show you. I've got here. It's a whole specialty in its own right, and we're just scratching the surface in a sense at undergrad level. It gets pretty heavy. It involves group theory, representation theory, and so forth. So just for your interest, like here are two books that I have. One's called Angular Momentum in Quantum Mechanics, and the other Elementary Theory. It's not so elementary. Elementary Theory of Angular Momentum. So, and what you can see there, sort of thickness, about 200-300 pages each. So this chapter will be sort of an introduction to how to add two angular momenta in quantum mechanics, and even at undergrad level, it's still it gets pretty tough, as you'll see in future sessions, right? So let's recap a little bit in what we've done already in the simplest case, when we just have to say let's say one electron, a system with one electron. Then it's a one angular momentum, if you like. So we talk about a single electron. The symbol I use for electron is really just little e with a superfix minus for the charge on the electron. Okay, so a single electron in a hydrogen atom, it'll have angular momentum L, where little l here is an eigenvalue of the allowed angular momentum when you quantize it. The projections, the components of that angular momentum along the z-axis, call that projection M, and its allowed quantized eigenvalues will take two little l, whatever the angular momentum little l is, there'll be 2l plus one possible components of the angular momentum along the z-axis, which we usually just call little m, right? So m can take 2l plus one possible values, l, right? And these l's are integers. The z here has nothing to do with direction. In this context, it's mathematics. You know, this belongs to symbol, so L belongs to Z. Z's it's a set. So capital Z here labels the set of all integers. Right? Well, actually, it should be N. No, wait a minute, L. I think it should be N, the natural numbers. So, well, L's are integers, right? And the electron also has a spin angular momentum S, and it can take. It only has two possible orientations. So the M, if you like, of spin angular momentum will be sort of be that way. S will be that way or that way. So its orientation, when you project that to the z-axis, you'll get that orientation is called up, because only it's two. And when S is this way and you project it to the z-axis, that projection, that component downwards, spin down. Okay, so we've done this, and you do the math, and you get the eigenvalues for the spin as plus or minus a half the projections, the M. Alright? Now that's about as simple as you can get, sort of just one system. So what happens in more complicated systems where, well, for example, you might be dealing with a helium atom. So that's the helium nucleus. So an alpha particle is a helium nucleus. A beta particle is just an electron. And a gamma particle is a gamma ray, very hard, highly energetic electromagnetic photon. If you've heard of alpha, beta, gamma particles in the past, coined by Rutherford way back, early 1900s. Right? So the helium atom, so its nucleus consists of 2 protons, 2 neutrons, so He4, so 4 nucleons in the nucleus. And to balance the 2 positive charges, the 2 protons in the nucleus, you have 2 electrons. Okay, so 2 electrons. So 2 spins, 2 angular momenta. So even with the next simplest element, helium, you've already got to start adding angular momenta, right? Because you now have a multi-component system. So even with the second simplest atom, let alone all the others, God, uranium at 92 protons in the nucleus and 92 electrons, things get massively complex. Alright, so the helium atom, it has 2 electrons. Each electron has an orbital angular momentum and a spin angular momentum. So you've got four angular momenta there already, right? So the theme of this chapter, and we've done this a bit already in the previous chapter, is how to add angular momentum. So that's the theme of this chapter, right? So devoted to this question. So topic, how the addition of angular momentum, how to add angular momenta 1 plus angular momenta 2. How do you do that in quantum mechanics? That's what this is about. Now, before we get into the nitty-gritty, and it will get very nitty-gritty, meaning highly detailed and a little complicated. You've probably heard me use that term quite a lot. If you're not a native English speaker, the nitty-gritty means the fine details. Right? So we will introduce now a little bit of new notation. So you're used to L as the symbol for the orbital angular momentum and the corresponding operator, so L hat. You're used to S for the spin angular momentum and S hat for the spin operator, so the spin angular momentum operator. Okay. Well, now we introduce a new one called J. So the corresponding operator for it is J hat. And what is J? It's a generic, a sign of general angular momentum. So if you're adding 2 general angular momentum, so sort of like J1 plus J2, well, what could these J's be? Well, lots of possibilities. They could be 2 orbital angular momenta. You could have 1 orbital angular momentum and a spin angular momentum, or you could have 2 spin angular momenta. Okay? And J is the generic, general symbol for either. Right? So J could be either an L or an S, if you see what I mean. So J hat stands for either L hat or S hat. It's a generic, well, without the hat here, it's just the total, it's called the total angular momentum. Right? Alright, so as we did with L and S, via the correspondence principle, we assume that when you hat, you make J this total angular momentum, an operator, you put a hat over it, we assume we can do that inspired, motivated by what's appropriate in classical mechanics. That's the essence of the correspondence principle, right? So let's assume that, that there is some operator corresponding to a general angular momentum, j hat, right? And let's say it has components along x, y, z axes, right, of this form. And then what we've done here for j, all the logic we went through for L, like when we had L plus minus, Lx plus minus I, Ly, and so on, all the way through to calculating what the eigenvalues should be, that lambda should be L into L plus 1 h bar squared. All that logic that we did in chapter, what was it, 6? Anyway, 6, 7? I'm losing track. we're up to lecture 9 now, so after a while things start to merge. Okay, but anyway, all that logic that we did earlier for L applies for, well, we assume applies for J, right? So we have raising and lowering operators for J. This is highly analogous to what we had before for L. Okay, and instead of having little l here, we have little j. Okay, so that's the light eigenvalues for the, what would it be? The j squared operator, I guess. Okay. All right. So so we're setting up a new notation now. So memorize this. That when you see an L like this, think of that L now as orbital, in an orbit, orbital angular momentum, and think of S as the spin angular momentum, and think of J now as the total angular momentum. So this J would be like the sum of these two, in a sense. And where J1 could be spin or orbital angular momentum, similar for J2. So the number of combinations you have here, well, there's 3, right? So you could have orbital, orbital, orbital spin, or vice versa, the same thing, or spin, spin, right? So the J is just usually, in words, referred to as the total angular momentum. Okay, so that sets up the notation that we will use from now on. So in all the math and so on in future sessions, it'll be we'll be using largely the J, this J notation. And what is J, like these raising operators, J plus minus, they increase. If you apply this to an eigenstate of, let's say, an eigenstate of the JZ operator, that's the component of J along the z-axis. Then, so if you apply, say, J squared to J plus of a eigenfunction, then you'll get this J plus here will raise the value of the it'll raise the eigenvalue by 1, multiple of 1. Now I'm being a bit vague. We've done this sort of thing before, and the J case is very similar, and we'll cover it in greater detail in the next sessions. But so the raising, the J plus, and the lowering operator, J minus, it raises or lowers the eigenvalue and changes the state to the lower state. If you're talking about energies, it would change it to a state. It would change a state to a lower state with 1 unit of lower energy. Or if it's the plus, the raising operator, it would change the state to the next higher energy state with corresponding higher eigenvalue, energy eigenvalue. We've done that before, so it's sort of revision. Except now we're working in the context of adding angular momentum, right? Well, we're setting up the notation, and then we can In the next session we will start doing a bit of the math.